Welcome back, everyone. So today we're going to be doing the last bit of topic 4/14, which is atomic orbital overlap. Atomic orbitals are of different atoms overlap with each other. Essentially, orbitals overlap when you do covalent bonding, and they form these things called molecular orbitals. Now, we can actually derive some of these by ourselves, I suppose. And what it amounts from is that here, let's take a sidetrack over to physics for a moment. Um, Erwin Schrödinger described the electron as a standing wave around the atom, right? And when we do covalent bondings, obviously those electrons behave slightly differently since they're bonded to two atoms and attracted to two nuclei and not one. So therefore, the shape of that standing wave will change quite considerably. Now, what since the electron is a wave and both a particle, if we consider the wave properties for a second, waves can undergo something called interference, and uh, for essentially you could have two types of interference: constructive and destructive interference. Constructive is when two crusts or two troughs meet up together to make a bigger crust or trough, and destructive interference is when a crust and a trough meet together to make absolutely nothing. So let's draw some of these out. So I'm going to focus on the SP one. The Sp2 and Sp3 are quite similar in logic. So let's say we have an S orbital, which we know is the shape like that, and a P orbital, which is the shape like that. And since the wave function has values, I'm going to arbitrarily assign them positive, positive, and negative, just because I can. And what will happen is when these two positive ends meet, you will get something that looks like this. So SP hybrid. If we do that to net that. Or alternatively, let's do this in red. If we did put this here, we essentially get we get a net result of this plus. Because this plus and this minus will cancel out to make nothing. You'll get a half a p orbital. I don't know, but you never actually see the destructive one in practice. What you do see, however, is this sp hybrid, and this would be sort of where the electron. This is where the nucleus is. So where the nucleus lies, and this is the bonding orbital. This is the non-bonding one. So that's important to note for later reasons. But that's sort of the, I suppose, principle behind atomic orbital overlap and molecular orbitals, the formation of molecular orbitals. That's sort of the idea of what I want to get across. So if we go back to our notes here, the above problem has been solved with the development of a newer orbital involving the hybridization of atomic orbitals. This is a theoretical model based on quantum mechanics that describes results related that which the results provided match with Esper theory, and that's sort of what I just described pictorially there. And I just did sp hybridization. One interesting thing to note is that when orbitals hybridize, at least for carbon anyway, one of the electrons, if there's an empty p orbital, i.e. there's a p orbital with no electrons in it, an electron from the s orbital will excite to fill that p orbital, and you can have, well, two unhybridized orbitals and an sp hybrid orbital, which is said to be of degenerate energy. It's sort of meant to average out the energy between an s and a p orbital. Sp2 hybridization works on a similar sort of basis, and if I were to draw this out pictorially, you would get something like, here's two p orbitals. Oh, shit, stupid. Oops. You would get something like that. Plus, plus, minus, minus. Let's say plus, and you'll get something that works sort of to form something like that. You'll form something like that with sp2 hybrids. that's sort of the idea behind the sp2 hybrid, and you can see here you get 3 hybrid orbitals. Um, Let me just delete this stuff here first for my paint. Right. Now that's gone. You get a similar sort of idea there, and these sp hybrid orbitals arrange themselves in an arrangement that's 120 degrees apart, and similarly these 2 sp hybrid orbitals will arrange themselves in a configuration that leaves them to be 180 degrees apart. So that is in line with VSEPR theory. Sp3 hybridization is a bit trickier. It sort of like forms in the corner. It hybridizes in the corner, and then you get 4 sp3 hybrids, and the 4 sp3 hybrid orbitals will combine to form a tetrahedral shape, again in line with VSEPR theory. There is a much to summarize. Now you might get questions that ask, okay, which carbon is sp3 hybridized? If you were to go through this process, it's obviously very tedious. So the easy way to remember is that sp2 has 2 electron domains, sp2 has 3 domains, and sp3 has 4 domains. You can just take the number of p orbitals plus 1, and that's how many electron domains there are. That's sort of little mathematical formula works for a lot of the multiple choice questions on IB. So as you can see here, 2 linear 180 sp. This little table here is what you're really, I don't know if you were expected to memorize this, but it's a good thing to remember, this little table here. The reason that there is a reason that these hybrid orbitals match so well with VSEPR theory. It's because an atom with hybrid orbitals, the hybrid orbitals contain valence electron pairs, and these correspond to electron domains, as we did with VSEPR theory. So there is a reason for the coincidence. I should say it's not coincidental. There's a reason for it. So this is sort of the atomic orbital overlap from sp3 with hydrogens. As you can see here, those are the little unhybridized orbitals. And then lastly, we talk about 2 types of covalent bonding that are the result of atomic orbital overlap: sigma and pi bonds. Sigma bonds are covalent bonds for which the overlap of atomic overlap of atomic orbitals results in the electron density concentrated in the axis of the bond, whereas pi bonds, it's outside of the axis of the bond. Now, what do I mean pictorially? What do I mean? Let's draw some pictures here. So let's draw. So here is a 2 sigma bonds. Here's the nuclei, and if they bond, so say the overlap, it's on the axis of the nuclei. So here is that. Here is the intermolecular bond axis, and the electron density is concentrated here. Whereas with a pi bond, if I draw 2 dumbbells, okay, hang on, let me do a better job of this. So you're going to have to forgive me for my really bad drawing. Here's the axis of the bond, here's the axis of the bond, and as you can see here, the region of overlap is here and here, which is not on the axis of the bond. So that's what a pi bond is, pictorially. Oops, wrong source. Right, now let me erase this. Select all, delete. Alright, so consider C2H2 as an example. This is the Lewis structure, and as you can see here, this is sort of the orbital diagram. So these H's only have an s orbital, so these form sigma bonds with this p orbital, whereas the other 2 p orbitals don't partake in the bonding, and they take apart in the triple bond. They take apart in the bonding. So this is a sigma bond here, and then these pi bonds here cause the interaction. What's important to note is that a double bond is actually the overlap of an s and it's a p orbital bonding and an s There's a sigma and a pi bond in a double bond, if that makes sense. And a triple bond, there's a sigma and a sigma and two pi bonds. So here's the first bond. Here's the second bond between this p orbital, and the third bond is between this p orbital, which is, perpendicular to this p orbital. So if that makes sense, that's important to note. And then molecular orbital theory, an atomic orbital was defined as a mathematically defined region of space where there was a certain probability of finding an electron. And a molecular orbital is no different. It's just spanning two or more atoms where there is a certain probability of finding an electron. All of these covalent bonding models which you've used so far works on valence bond theory, which only considers atomic orbitals, but it's limited to localized electron models, whereas molecular orbitals account for things like delocalized electrons. In essence, the process of bonding actually changes the orbital of the atoms involved in the bonding, so therefore you get molecular orbitals. So the difference is that when applying molecular orbital theory to two or more bonding atoms, the resulting orbitals are molecular orbitals, one atomic orbital. From each of the two bonding atoms combine to make two molecular orbitals, a bonding and an anti-bonding orbital. The bonding of one is of lower energy, the anti-bonding one is of higher energy, and the two shared electrons within the covalent bond reside in the bonding molecular orbital, which makes sense because that's where they bond, right? So here is sort of an example of the sigma bond in the H2 molecule. So this is the bonding orbital, this is the anti-bonding orbital, and again, here's this sort of, and here's something that signifies. So here, these are the 1s orbitals. They combine to make a lower energy orbital and a higher energy orbital. The lower one is where they bond, the higher one is where they don't, and that's sort of that. And yeah, that's it. Thank you so much for watching.